You ever stop and wonder what really powers our modern world? I mean, we're surrounded with all this incredible tech, right? But the actual stuff that makes it all work, well, that's usually a total mystery. So today, we're going to pull back the curtain and take a look at these secret ingredients.
Okay, so think about this for a second. What could possibly connect your phone screen, a giant wind turbine, and a train that literally floats on air? I mean, on the surface, they've got nothing in common, right? But they do. They all share this one secret ingredient, this hidden connection that's totally essential to how they work. Any ideas what it is?
Well, the answer is a really special family of elements. Now, you might have heard them called rare earth elements, but that name's actually a little misleading. The thing is, it's not that they are super scarce in the Earth's crust, it's that they're a real pain to separate from each other. So getting a pure sample of just one of them, that's what was truly rare. And wow, as our tech has gotten more and more advanced, the demand for these things has just exploded. Check this out. This chart shows the price for just one of them, dysprosium. It's a key ingredient for the powerful magnets you find in electric cars and wind turbines. And look at that price jump. From 2008 to 2014, just 6 years, the price more than quadrupled. That right there tells you everything you need to know about how vital these materials are to us now.
So, what are we actually talking about here? What's the real name for this family of miracle ingredients? It's time for the big reveal. We are talking about the transition metals.
Okay, transition metals. I know, it sounds a little technical, but the secret is all in their electron structure. So here's the deal. Imagine electrons zipping around an atom in different layers, or orbitals. For most elements, those outer layers are either totally full or pretty much empty. But transition metals, they're different. Their outer d orbital is only partially filled. It's this in-between state that makes them so incredibly flexible and gives them all their amazing powers.
And if you picture a periodic table, you literally can't miss them. They're that huge block of elements right in the middle, from groups 3 to 11. That's the D block. But that's not all. They also include those two separate rows you always see at the bottom. That's the F block. That's where you find the lanthanides, with elements like europium that makes your TV screen light up, and also the actinides.
All right, so we know what they are and where they live on the periodic table. But the real question is, what can they do? Let's talk about what makes them so special. Let's talk about their superpowers.
Okay, so for starters, they've got all the classic metal properties you'd expect. They're strong, hard solids that don't melt easily. They're amazing at conducting heat and electricity. And they're fantastic at mixing with other metals to create alloys. Think iron and carbon making steel. Oh, and they also form some absolutely beautiful, colorful compounds.
But look, that's just the basics. That's not the main event. Their true superpower, the one thing that really truly sets them apart from everything else, it's their unbelievable chemical versatility. And this right here shows you exactly what I mean. Just take a look at manganese. A simple metal, like sodium, pretty much only has one chemical mood. But manganese? It's a chemical chameleon. It can exist in a whole bunch of different states. You can think of these oxidation states as different chemical personalities. And this ability to swap personalities means it can get involved in all sorts of chemical reactions, which makes it an incredible catalyst.
This versatility also means you get this huge range of reactivity. On one hand, you've got metals like iron, which rusts, oxidizes, pretty easily. But then, on the complete opposite end of the spectrum, you have platinum and gold. They basically refuse to oxidize. And that stability is exactly why we use them for things we need to last forever, like your wedding ring or the critical circuits inside your computer.
So we know what their powers are, but how did we, as humans, figure out how to use them? Well, let's get into their origin story, because really, it's the origin story of civilization as we know it.
I mean, our entire history is defined by our relationship with these metals. Think about it. The Bronze Age, that was us figuring out how to isolate copper and mix it. The Iron Age, that was us inventing the tech to smelt iron from rock. Every single step was a giant leap for humankind. And today? Well, today we're in a totally new era, refining a whole bunch of these complex metals for the highest of high tech. And, the funny thing is, the basic way we get a pure metal out of the ground hasn't really changed all that much, at least in principle. It's basically a three-step process. First, you dig up the ore, crush it, and get it concentrated. Second, you smelt it. You hit it with a ton of heat to separate out the metal. And third, you refine it to clean it up and get rid of the last few impurities. And if you want to see this in action, there is no better, more iconic example than the blast furnace. It's been the roaring, fiery heart of iron production for centuries. Just think of it like a giant industrial-sized recipe. You dump your ingredients in the top: iron ore, coke, which is basically just a type of carbon, and limestone. Then you blast superheated air in the bottom. That hot air turns the coke into carbon monoxide gas. Now this gas rises up through the furnace and literally rips the oxygen atoms right off the iron ore. What you're left with is pure, molten iron pouring out the bottom. And the limestone? That just grabs all the other junk, creating a waste material called slag. It is truly brute force chemistry on an epic scale.
Okay, so we've covered what they are, what their superpowers are, and how we get them out of the ground. Let's bring this all full circle now back to where we started and talk about the real payoff, how these incredible metals are building our future right now. And one of the most mind-bending applications has to be in superconductors. Now, the idea itself is pretty simple, but the consequences are, well, they're world-changing. A superconductor is the material that can conduct electricity with absolutely zero resistance. Zero. That means no energy has ever lost its heat. It's perfect efficiency. That alone would completely revolutionize everything.
So for decades, this was just a lab curiosity. Superconductivity only worked near absolute zero. We're talking the coldest temperature possible. And you needed crazy expensive liquid helium to do it. But then came the breakthrough. Scientists discovered these special ceramic materials, all built around transition metals, that could do it at 90 Kelvin. Now look, that is still ridiculously cold, minus 298 Fahrenheit. But in the world of physics, that's a high temperature. And it's a temperature we can easily reach with cheap, everyday liquid nitrogen. That was a total game changer. And suddenly, the door was blown wide open for all these incredible technologies. Imagine it, power grids that don't waste a single watt of energy. Trains that float on magnetic fields, MRIs and microchips that are way more powerful and smaller than anything we have today. Heck, even the magnetic bottles we need to finally crack fusion energy. All of it depends on the unique superpowers of these transition metal compounds.
So, when you think about it, from the very first iron tools that changed human history, all the way to the mind-bending quantum physics of a superconductor, transition metals have been there. They've been the secret ingredient every single step of the way. They are, quite literally, the elements that build our world. So the only real question left is, what new age will they help us build next?